So basically on Thursday, my friend is going to come over from the Army water and he's going to give a presentation on RSA and breaking value competitions for RSA. With the community to
Did you make a sign-up sheet? No,
no, just people show up, like people will sign up and then they'll show up over the
so we're back in calculus. And last time we did a detour side quest to talk about to define the trigonometric functions as we did. And we basically shown everything about the trigonometric function that is learned in high school. And next, we're going to see something that is not being taught in high school, but still geometric, trigonometric, and then we will see why are we talking about it. So I'll write something of what I said. We will see a geometric, we will have a geometric discussion. Hi, Sammy. And we will have a geometric discussion whose results will be made clear later. What I'm trying to say is usually we present a claim and then we prove it. Here we're just looking at some geometric building. I'm not sure how to say it. So, some kind of a geometric argument, and we'll get an equation out of it, and that equation is really important for the future. Structure, I think the word I was looking for.
made with like
Yes. Yeah, the maid makes made it clear. The maid made the window clear. Okay. Thanks. So our structure will be, I need to reopen it because I reset my computer, but it's saved, so that's fine. And okay. So I prepared the structure ahead. So I will just explain what that structure is. Given an angle x between 0 and half of pi, we study the following geometric structure. And what the structure is, the red line is the unit circle. The point A here, is the point cosine of x sine of x, which means that the length of the arc here is x. The length, I'm not sure why is it not here. I'll recopy the picture. So by definition, we said that if the angle is x, the length of the arc AB in the unit circle is x. The point here is cosine of x sine of x. And we take this perpendicular line here, whose length is sine of x. The length of the edge OB is 1. Why is the length of the edge OB equals 1? OB.
Oh, the unit circle.
It's the unit circle, it's the radius. What is the length of the edge OA?
Also one.
Also 1. We continue OA and we lift a perpendicular line from B until the two lines meet at the point C. Okay? So that is the structure we are looking at. Again, it is not clear in general. Why am I looking at this specific structure? It will become, it will be explained soon enough. Okay? There are 3 shapes, areas in this drawing which we care about. Yes.
So that's why tan is infinity it's undefined at x equals
Yeah.
because the parallel lines.
Yeah, that's I'll tell you something, Sammy. Always I argue with myself, is it better to create with you the drawing or just put it out there? You just prove the shortcoming of that you're looking at the stuff I wrote ahead, but for now you're not supposed to see. So yeah, you're seeing the tan here, but why is it written there? I will prove in a while. What's better about building it, that's what's better about building it together, but that takes time. In any case, yeah. The length of BC in response, direct response to answer is the tangent of x, and as x goes to pi over 2, that length goes to infinity. It's exactly that. That's the geometrical interpretation of the tangent. It's also a reason, if you put the spotlight on it, why is it called the tangent, Sammy? What does the word tangent mean?
It's tangent to the circle.
Yeah, exactly. Mashik in Hebrew, because it's tangent. Yeah. So then it's something nice. You don't usually see it because it's not that important. I only show it in this specific proof. But I do need to reiterate that it's not clear at all why did I write tangent tan x here. We will see it. Okay. So the 3 areas that we care about here are the area mark 3 areas. S1 would be the area of the triangle OAB. Okay, you see the triangle OAB. So let's call this area S1. S2 would be the area of the section OAB. What's the difference? I wrote here OAB and here OAB.
It's inside of the arc.
Yeah. That is the pizza slice with the crust. Okay, if you're looking at the pizza slice OAB, then the section in Hebrew Gizra would include that part here, which is the crust of the pizza. Okay? S3 would be the area of the triangle OCD. Okay? Let's zoom out a bit so we can look at everything at once. So we have that triangle over here. We have the section of the circle together with the pizza crust, and we have the big triangle. What is the connection, the geometric connection between these three shapes?
So
They are inside each other, right? So S1 stands these areas are included in one another. S1 would be smaller than S2, which will be smaller than S3, and they are all larger than 0 as well. Agreed? So we will calculate these areas, and then we'll get an inequation. That inequation is important to us, and then we will see why I do all that I did. Okay. So, and 0 is smaller than. What is S1? What's the area of the triangle AOB? It's the height sine of x times the base over 2. The base is 1, so it's sine of x times 1 over 2. Agreed? Next. What would be the area, the section of the circle? So what is the area of the entire unit circle? Pi. The circumference is 2 pi, the area is pi. That requires a proof by itself, but we're not delivering it today or at all. And what is the what is the relative size of the section?
X over pi.
So it's x over the entire circumference. It's the part of the angle out of the whole square. Here comes the difference between radians and degrees. If the angle were to be measured in degrees, what would I write in the denominator here? 360. And then we will get pi over 360. If we take the 2 out, it will be pi over 180. We had the discussion last time. But if I'll do it with the actual circumference, it's x over 2 pi, and the pi is, and that's why we are left with no pi here, and we get in this inequation, the pi cancels out, but this inequation gives rise to the derivative, and probably today we'll derive sine function using this inequation. Okay, and lastly, that one requires some calculation. Why? Because the area of the big triangle is the edge CB, which we don't know yet, Sammy, times the radius, the base, which is the radius 1/2. So I'll just write for now OB times 1/2.
Sine x over 2 again,
What?
sine x over 2,
What's sine x/2?
if that makes sense.
Isn't that what you want?
Sorry, no, sorry, so it's tan over 2.
No, it's OC times 1/2.
It's BC. It's BC. Okay. That's what my mistake. Sorry. Yeah, it's BC. It's the height. The height is BC times 1. Yeah, because I said OB, I wrote OB. OB is 1. Yeah. Okay, thank you. But what is BC? We can use the ratio within right angle triangle, because COB is a right angle triangle. So CB over OB opposite over the adjacent TOA, right? It's the tangent. The tangent of X is BC
You're missing out the fact.
over OB.
You're missing out the fact that just because they're right angle triangles, it's just similar.
Similar to who? I just use this triangle, not two triangles, just one triangle. I'm just looking at OCB, and in every right angle triangle, the angle here is X. So the tangent of X is the opposite over the base. And what's special here is that the base is 1. And what does it mean? So BC over OB, that's BC over 1, which means, therefore, BC equals the tangent of X.
Oh, I did completely different way.
Because-
I didn't not assuming like even knew what tan was.
Yeah, you use the proof from last time that similar triangles have the same ratios, and then you did, but we proved that it's always the case. Therefore, always the ratio between the opposite and the base is the tangent. So that's what I use directly. So that's why BC is the tangent, and everything we said before is tangent line, and when the angle turns to pi/2, then the length of the tangent go to infinity.
What is the definition of tangent? The definition of tangent is
Sine over
x
cosine, yeah. Here, CDF, that's the definition, okay? And we proved last time that it's the opposite over the adjacent. Okay, so all together, and multiplying by 2, we get that for every x between 0 and pi/2, where this structure is possible, then sine of x is smaller than x. Look, I multiplied by 2, so all the 2's here are cancelled. So we get here sine, we get here x, because the pi cancelled out, and the last one is the tangent, which is smaller than tan of x. Agreed? Yes.
Do you call them pattern? Because they're not functions.
Who is not a function?
Sine, tan, cos, because they're not one.
Sine
The ones
is a
that-
function.
They're one to many.
No. They're many to one, not one to many. There are functions. For every x, there is a single y value of sine of x. They're not one to one, but they are a function. You're thinking about the inverse. The inverse of sine is a problem. The arc sine, and then we reduce our domain so they become one to one to certain angles. Okay, so we got this inequation. If I would have started this subject like usual, I would say claim for every x this inequation holds, and then the proof. But like I said, no one would think about that proof or that theorem, so I like to start with the geometric structure. But that is what we need. It's not clear yet why do we need it, but we passed that hurdle, and from that moment on, I think we'll have no more geometry in this subject. We just needed this inequation, and you'll see what are the results. Result one, I'll call it. The limit when x goes to 0 from the right-hand side of sine of x, what is it? And why is it a result? Look at this part. When x goes to 0, what is that? What is that? 0, x goes to 0. This goes to 0, and this goes, it's truly it's x. This goes to 0, and this goes to 0, so why? Sandwich, exactly. Next one. Proof
So says.
whereby stand which. What did you ask, Sammy?
Said, but that makes no sense.
What makes no sense?
This is.
Dear man,
Wait.
you made no sense today.
I think the answer, like, this is between 0 and half pi. I think
If I don't mind, then that makes sense.
You thought sine at 0 is 1 or something? Sine is 0, it's actually 0. Since result 2, since sine of x is an odd function, the limit from the left-hand side is the negative of the limit of the right-hand side. I never proved that as a general theorem, but that's like an exercise type of theorem. And that's minus 0, which is 0. So so together the two-sided limit of sine of x at 0 is 0. And what does that tell us? I'll hint. It's also the sine of 0.
So the limit of sine at x equals 0 is 0. That's like because it's left and right. That's what.
Yeah, but what does that tell you?
Um,
What do we call that equation here? Exactly. So sine is continuous at 0. For homework, show that sine is continuous everywhere. continuous everywhere. And I'll give you a hint. And sine of x is, I'll write, and the limit as x goes to x0 sine of x equals the limit as h goes to 0 of sine of x0 plus h. You see why? If I put numbers close to x0 here, it's the same as substituting instead of h numbers close to 0. And why is that helpful? Why is that conversion helpful? What? No, it's not linear arithmetic because you have sine of x0 plus h, right? Sine is not a linear function. But was it sine of x0 plus h? What with identities? Sine of x0, cosine of h, and so forth. You're welcome to it. Okay. And then you get its okay. And also result 3. What is the limit as x goes to 0 cosine of x? Why?
It's from both sides, so because it is sine.
You multiply it through by cos. Right, yeah.
You think of the equation. It's easier than that. Cosine of x equals to square root of cosine squared of x.
Of course.
And I need to it's not, you do need to say something else about it. Since say note and note at an area of 0, cosine is positive. So we need cosine is the x value, and the x value is to the right. So we need it to be positive to say it's the square root of cosine squared. If cosine was negative, then it was minus the square root, and we'll get the different result. In any case, this is the limit, this equals the limit as x goes to 0 of the square root of 1 minus sine squared of x. And now we use limit arithmetics because we already proved that the sine goes to 0. So it is square root of 1 minus 0 squared, which is 1. And we can get that cosine is continuous as well. I don't mention it because it's similar to sine, but I did need that limit. You'll see in a few seconds. Result 4. Again, if x is between 0 and pi over 2, we know that the sine of x is smaller than x, but that's smaller than the tangent of x. What is the tangent of x? That's the sine of x over the cosine of x. Agreed? Who can tell me the next step? No, not the next conclusion. What will be the next algebraic operation? If you have any guess.
Everything by cosine.
No. It's close, but no. We'll divide everything by sine. So 0 is smaller than 1. It's not needed anymore. 1 is smaller than x over sine of x, which is smaller than 1 over cosine of x. Agreed? dividing by sine of x, get the following. Agreed? When x goes to 0, where does this end?
Zero.
That's a trick question. 1, it's a constant, right? But where does this tend when x goes to 0? Also 1, because we proved it a minute ago, right? So again by sandwich, the limit as x goes to 0 from the right. Why from the right? Because the whole equation is just true for positive x's near 0. Then we get the other side using the fact that a function is odd or even of x over sine of x. And what does that equal? And now it's an awe-inspiring moment. 1. That's very important. Since if f of x is x over sine of x, what is f of minus x? Minus x over sine of minus x, right? Yeah, which is minus x over minus sine of x, which is again f of x, right? It's an even function. That is an even function. So the two-sided limit exists. It's the same. The limit from the left is equal to the limit from the right, which is 1. And lastly, we formalize the result in the following short theorem, short to describe the result. Theorem. The limit of x goes to 0 of sine of x over x. What does that equal to? You see the difference between the limit written here and the limit here? That's x over sine of x, and that's sine of x over x.
So 1.
It's also 1, yeah, it's technically 1 over 1 using arithmetic. It's the inverse, right? But it's 1. No, just write 1, okay? I'm not sure what reciprocal is. Inverse multiplication inverse, right? If one was 2, the other one was half.
That's so I don't know, in English we say that's the reciprocal.
Okay, okay.
Like you have a fraction, you take
The reciprocal.
numerator.
Okay, okay. In mathematics in general, from fields, it's the inverse, right? Multiplication inverse. But yeah, whatever you said is true as well.
I don't
Yes.
see limits and exponents, right?
What?
We didn't study what does exponentiate.
I showed you that in the math wiki there are hints to how to prove it yourself, but I did claim that arithmetic of exponents works as well. Okay, because you say 1 over. It's funny to me that you're asking it now. We just used it on a square root a minute ago, which is much more complex, right? Now we can use it because we did prove quotient of two limits. So 1 over is a quotient. You don't need to think of it as an exponent. So it's silly. But here it is an exponent, and here the question was just as unnecessary to find. But yeah, actually proving for the exponents is a bit of work. In the math wiki, there is a way, even for the math majors, I don't go over the entire proof, it's a waste of time. But yeah, we can use limit arithmetics with exponents. Okay, and we do. With the E, it's your catchphrase, yeah, I've never seen it in my life, it's because we use it in the E law as well, right? In the E rule. Okay, in any case, that is a theorem. Quick, quick note. What is wrong with the following shorter, much shorter proof for this theorem? I'll show you a proof using a tool which we didn't learn yet, we will in the future, that's not a problem. The numerator, where does that tend? Sine of x, where does that tend? 0, and the denominator?
0.
0, so which rule can we apply? L'Hopital, which gives us, and whoever is not familiar with L'Hopital rule, it means that when we have 0 over 0 or infinity over infinity, we can take the quotient of the derivatives instead of the original function. So instead of the quotient between sine of x and x, we take the quotient of their derivatives. What's the derivative of sine of x? Cosine of x. And what's the derivative of x? 1. So what's the limit here? 1. Isn't that nice? Why did we went through all these troubles? All these troubles where apparently L'Hopital solved it like that.
Not telling you what the derivative of sine x was.
Yeah, and how do we calculate the derivative of sine of x?
By using what we just proved.
Yeah, exactly. That's the main thing. One can also say that we use here that sine goes to 0 and cosine goes to 1, which we also proved using the geometric tools. But even if I accept these limits, still we use the fact that the derivative of sine of x is cosine of x, which uses the result of this theorem. Thus, we get a circular argument. Okay, so in the test, if you for some horrible reason forget that sine of x over x goes to 1 when x goes to 0, you can use L'Hopital because by the test it's true, it's a mathematical fact. But for the lecture, I couldn't use L'Hopital here because even if I did skip the trigonometric functions and prove L'Hopital, my problem would be why is the derivative of sine of x cosine of x, and we will see it in a bit. Okay. Another note. What is the limit when x goes to infinity of sine of x over x? Why? Exactly. Bounded over infinity is 0. Okay, so a lot of times students confuse that and always see sine of x over x and say 1. When x goes to 0, it's 1. When x goes to infinity, it's 0. And sometimes it's important if that's the exercise. Any questions so far? Okay. And next, we've finished with now we are back to our scheduled programming.
Well, to do this,
IA. What?
you want to do this.
No, not exactly. We were supposed to do it, but what I mean that it was a detour. Because we stopped, it wasn't really calculus. It was geometry, trigonometry, right? The whole story of calculus was we have limits, not the whole thing, but in functions, we have limit of functions, then we have continuity. What should be the next step? Derivatives, exactly. So I just thought the trigonometric functions there, you see why, right? But yeah, it's like it's a side note, but it is part of the material you should be familiar with, right? Okay, i.e. derivatives. First, the discussion, introduction. What makes philosophically what makes philosophically a function differentiable? What is the derivative? These are the questions I wish to discuss. So can you answer any of these questions? Yes, Sami. What again? Come again?
It has to be continuous.
That's true, but it's not enough. So that's not, it doesn't make it differentiable.
It's more of a property,
It's what?
more of a property than.
Yeah, but what if you see two graphs of function, how can you tell which one is differentiable and which one is not?
Has a gradient at every point.
As what?
It has a gradient at every point.
Gradient, you said?
Yeah, gradient, like
Slope, you mean?
Yeah,
Yeah.
But okay, so what does it mean to have a slope? But that's not true. Forget continuous, that's false. Say the entire discussion takes place about continuous functions, and we wish to separate them into the differentiable ones and the non-differentiable ones. It's not continuity again, it's a whole new subject. You can't just say
They
continuous.
have non-differentiable continuous functions.
Obviously, yes. Otherwise, it wouldn't be.
Yeah, obviously.
No, because otherwise it wouldn't be another subject. It would be, let's call continuity by a different name. Right? It's something different. That's why I'm saying it's obvious. It's not obvious because the definition that I didn't give you. It's obvious like through the lesson. It wasn't, it's a different subject matter, so it's not the same. So try. The first question is kind of hard. Let's try the second one. What is a derivative? Okay, so you'd say, no, not exactly.
I'm not 100% correct.
Of f, no, you just didn't answer the question, you'll see. The derivative of f, it is a true statement, is the slope of the function f at a given point. Then what is the slope of a function?
Okay, so the derivative.
The derivative, yeah, and that's circular, yeah.
they depend rate of change.
And that's not a definition, you're correct. The what?
The limits.
No, I'm not looking for the mathematical definition. I'm looking for a more geometrical definition. By the way, what Thomas gave me was a rather physical definition. It's the speed, right? The velocity. It's a very acceptable way to think of it. It's probably the way it was invented because Newton did it. but I'm looking at a more geometric interpretation, which is very important.
Over X.
No,
Okay, you get.
and I'm hinting at when you look, okay. I stop hinting and I'll show you. I'll show you a few, not the definition yet, but I'll show you a few function, sorry. Look at x cubed. Is that function differentiable?
Yeah.
Okay. Look at the absolute value of x. Is that function differentiable? At 0. Okay, what I'm trying to say that with your eyes you can see it in a second. You're not calculating limits. There is some property that you are able to see and say whether it's differentiable or not. And now I'll give you what?
That isn't differential.
No,
Why not?
Because.
we'll see in a bit. And lastly, the third root, the red line. Would you say it is differentiable at 0 or not?
Sure.
So it's not, by the way.
Yeah.
But it looks differentiable. That is like the I don't know. That's why mathematical definitions sometimes don't encapsulate the philosophical idea perfectly. For the philosophical idea, I agree with you. Both the red line and the green line look both the same. They're actually a reflection of one another with a mirror placed at y equals x. You see, the green and the red are just reflections of one another, so it's inconceivable that one would be differentiable and the other is not. And yet that's the case because of the definition we will give.
Does it have
But
to do with having a valid point?
the what?
Okay, no.
No, I didn't hear you. Could be the
No,
right.
I already realized I'm wrong.
Probably. Okay.
On average, yes.
Yes. On average, no, okay. That's the way we grade the paper. Just assume that you failed and don't waste each other's time. So the function is a function. So after I said that, I'm getting back to what is the slope of the function? What is the slope of a function? So slope in general is the rate of change in a linear function y equals mx plus b. The rate is constant m. What about any other function? And again, philosophically, geometrically, what would you say the rate of change of the function is? And let's get back to the example. Start with the green one. What is the rate of change? At 0? What would you say? 0. At the absolute value, what would you say the rate of change here at 0?
No.
But it's not 0, right? What is the rate of change here?
Undefined.
Yeah, it would be undefined because it's -1 to the left and then it's +1 to the right. Okay? And what would you say about this? What would be the rate of change here? Infinity. That's the reason it's not differentiable, because by definition we would need a finite rate of change, and once it's infinity, it's considered undefined. And defining it as infinity creates a few philosophical problems.
Is it the graphs that are derivative of the function of the derivative has to be continuous.
If a function is differentiable,
It's
it's continuous, but the derivative itself does not need to be continuous. So we'll see an example later. Okay, so, but again, what makes this differentiable geometrically?
slopey.
What do you mean that it's slopey? It looks like near zero.
It has
If I zoom in,
the rate of change, the rate of change changes.
if I zoom in near zero, what will I see?
It's just like that.
What does the function looks like?
Hence,
No, but is the function? If you were to describe this function,
it's like a flat line.
it looks like a straight line, exactly. And what does this line? What is this line called? The tangent. That's the tangent. Okay, so answers now after all the questions.
So you can draw a tangent at any point. No.
Philosophically, a differentiable function is one that looks like a line when zooming in. It's not a good definition. It's not the mathematical definition, but that's the idea. It's important to understand that this is the idea. What about the red function here?
Y equals x, then, oh, I see, a line of zero, okay.
What about the cubed root? It's the red line here. Does that look like a line as well? So it ought to be differentiable, but it's not because it's, like I said, the slope, it's not a function. This red line is not a function, the slope is infinity, that's a problem. Okay, so philosophically, I would expect it to be differentiable. You see what happened when I zoomed out? We would expect it to be differentiable, but it is not by definition. Okay? And lastly, if I take the absolute value, what happens when we zoom in? See the difference? It does not look like a line. It remains as a point, not point. It's tell me when to stop.
This one. If you're like the very, very end.
No,
There is no end. It will always remain as a corner is the word I'm looking for. I will. Okay. But yet again, it's not the mathematical definition yet, right? And
Yeah, right now we're looking about looks and feels.
yeah.
Like a line.
You're right, but it's important. Sometimes even mathematicians, it's hard for them to grasp that this part is important, how to actually use it. And when you look at the great mathematicians like Newton, they start from an idea. We want to grasp the concept. It's not enough just to look at the definition. We need to understand what they actually mean. It helps us to understand the big picture here. I will show you in a bit what I mean, but here we see x cubed in green, which looks differentiable and is differentiable, and the cubed x third root of x, which looks differentiable, yet it is not by the definition we will see. And the absolute value of x, which is not differentiable. Doesn't look differentiable and is not differentiable. Oh. To emphasize
Okay. Yes.
that's all, okay. To emphasize this idea, let's look at f of xy function with two variables. What would you say, what would you think makes a function with two variables differentiable? That's not part of the syllabus in this course. I think you study a bit about it in Phi2, in Calculus 2, but in general, it's important for me to show you now. Let's take a function f of xy equals the square root of 1 minus x squared minus y squared. That's a sphere, it's the top half of the sphere. Is that a differentiable function?
Yes,
Why?
because of there's no overlap, I think.
That makes it a function, not a differentiable one, right?
Hmm.
What did we say a differentiable function in one variable is?
A line.
Looks like a line, right? What do you think makes this differentiable? Exactly.
I think it's
If we zoom in, what does it look like? A plane. And that is called the tangent plane. The idea of differentiability is looking linear up close. And that is a super important concept that many times students don't get to grasp, because it's one of the things that makes linear algebra so important. Because in linear algebra we study linear stuff, and in calculus we basically say everything is linear. So great, at least locally, right? Everything is linear locally, and then you can use linear algebra. And in calculus 2, you actually use linear algebra tools and to ask things like, in which direction is the function going upwards? And because it looks like a plane, you answer this question for the plane. And it becomes a rather easy linear algebra question. You will see it in calculus 2. And it's important for data science, because in data science you have many variables, and you need to understand how to work with it. And the derivatives mainly assume this is a linear function, right? At least locally. And solving problems with linear functions is much easier. And that's what we do. Yes, sir.
Can you go back to the,
This?
can you type in
Yeah.
f of xy equals? Oh wait, can you do sine xy?
Yeah, sure. Oh, you're happy, Sally. Which is also differentiable. That's the nice thing. Zooming to wherever looks like a plane. Right? That's differentiability, says everything is the same. Everything up close looks differentiable. And lastly, if we look at the let's look at square root of x squared plus y squared. That's the cone. what happens when we zoom in to the origin of the axis?
Looks like a cone.
Still looks like a cone. It's not differentiable. And what does it look when you look at it like this? Like which function? The absolute value, because that's the generalization of the absolute value. It's like the absolute value rotated around the z axis. So that's like non-differentiable, and that's a non.
It's starting to scare me.
It's just starting.
Well, I'm discussing my lab for the last 2 months.
Yeah, you're growing Golda for me. Okay.
Ruined what?
Golda ice cream. It's a cone.
No, cones ruined the building.
Yeah.
Tell me what this is.
Okay. And that's this pretty picture. Let's put it as well. But that is more than you need to know, but it's important for you to understand the idea of differentiability is being linear locally. Okay, I'll write it. So the idea of differentiability is being locally linear. Okay. Now enough of ideas. Let's do definitions. But the definitions, as you will see, has a lot to do with the idea we wanted to grasp. Definition. We say that f is differentiable at x0 if I'll talk about the limit in a second. If I take the y difference at the top and I divide it by the x difference, if that was a straight line, I would expect, if the function looks like a straight line, I expect that to be the slope of that line, agreed? So when x goes to x0, that's the limit part, that means locally near x0. So if the limit of the slopes of the chords exists and is finite, and it's defined to be the derivative of the function at the point. So why am I saying it's the slope of the chords? You'll see in a bit. Note, we look at 2 points on the graph of the function. One would be x0, f of x0. The other will be x, f of x. The line segment between these 2 points on the graph is called a chord, and its slope is difference in y value over difference in x value. Agree? Okay? And I demand that it will be a finite limit. That's why the root 3 of x is not differentiable, because the limit here turns out to be infinity. And that's why it's not differentiable by definition. In absolute value, it's undefined. The limit does not exist. Okay? Let's look at an example. Take f of x to be the square root of x, and x0 to be 9. Okay. If 9 is too obvious, I'm changing my definition to 4. I hope it would be nicer. I think that's fine. So what's going on here? I'm changing it to 4. What's going on here? The blue line is the graph of the square root of x. I'm focusing my attention on x equals 4, that's x0. And I'm looking at the point of the graph, x0, f of x0, it's the red point, right? I take the second point, that's the gray one, that's x, f of x. And I take the line that goes through these 2 points, that's the red line here, and that's what we call the chord. We take the slope of that chord as the gray point tends closer to the red point, because we send x tending to x0. So first of all, I'll take one picture of that. And now I'll take the gray point and I'm tending it to the red one. Agreed? What can you say about the slope of the chord or the chord itself? What can you say about the chord here? It's way closer to what? Yeah, to be in the tangent, right? By definition, well, I'll write it. And definition, if f is differentiable at x0, the tangent line is defined to be the line with slope, which is the derivative by the definition we gave above, that goes through and the point passes through, but passes through the point x0, f of x0. So it's closer to the tangent by definition, but idea-wise, philosophically-wise, yes, that's the whole idea. The slope becomes tangent. We define tangent using derivatives, and we define differentiability and derivatives using the limit of the slopes of the chords. Any questions so far? What is the slope of the red line here? You can see it here on the side. It's 0.253. What would you expect slope to be? Why?
Yeah, it's one.
This is the square root of x. How do you know what is the slope at 4? What's the derivative of the square root of x? Yeah, 1 over 2 times square root of x. Since x is 4, it's 1 over 2 times 2, which is the quarter. 0.25 is the actual tangent line. And that's in green here, if you can see it. And it's really, really close to the chord, but really is relative. Here it looks close as well. And I don't think you even notice the difference. A bit, you see that I'm flashing at the red line. Okay. So this is the idea of differentiability. And before I move on, I want to give you another example. It's actually the one. Let's try to do it fast. F of x is if x is greater than 0, then sine x times sine 1 over x, otherwise it's 0, and a equals 0. Great. Okay. Okay. Now I'm going to play the gray points movement towards the red point. What would you say is happening to the slope of the chords? Does it have a limit?
Yeah.
0.
Look.
No, it's like.
Look what happens as the gray point reaches closer. Look what happens to the slope.
It goes to x equals y, so.
This is x equals 1.
Or negative x equals y.
This is x equals negative y.
So it's
It's jumping up and down.
yeah, it's
It's moving. Does not have any limit at all. That's a non-differentiable function.
Partial limits.
It's no, that's sequences. There is no two. There are no partial limits here. But actually, it's every value in between as well. So that's one of the reasons. Also, there is no limit whatsoever because
Like
it continuously jumps around.
you've got a highest gradient and a lowest gradient.
Yeah, that's true. But in any case, we would say this function is not differentiable. And I think when zooming in, it does make philosophically look it's sound, right? It does not look differentiable. I wish to put some picture of it. Scared by that, right?
Yeah, yes.
Okay, and yes. And another interesting thing is look at the function x squared here. What do you think about that? That's not constructive. What do you think about that? Is that differentiable?
Yes.
It is, because even though it jumps around, it tends to zero. But yet philosophically, one can argue,
They're the same.
does this look like a straight line when you zoom in?
Yes.
But it always jump up and down, right?
It jumps up, down, gets smaller, smaller, smaller as you do it.
Yeah, so one can argue about it. It's a very interesting case. But we will see that it is in fact differentiable.
Because of what it is, it's the original function isn't differentiable, but the patch function is.
No, it's not about the patch. I changed the patch function. The original one is not continuous because I cannot divide by x. But there is a difference. I changed the formula here. It was x before, not x squared. Okay. Okay. Any questions up to now? Okay. So now, our next example,
If you just go back up to the definition.
this one. None of you said it, but usually when asked what the derivative is, what is the slope of the function, then students answer the slope of the tangent line. And then my next question is, what is the tangent line? But since you didn't say it, I didn't get to tell you it's the other way around. We first define the so-called slope of the function, the derivative, and then we say the tangent line is the line with the same slope. And it does not fit perfectly with the philosophical idea, but good enough. Okay, yeah, maximum effort, like that would say. That one. Okay, example. Let's derive, the silly joke. Why does alcohol and mathematics does not mix? Because you're not allowed to drink and derive. Okay. Let's derive the square root of x. So you said it's 1/2 times the square root of x. How did you know that? You remembered from high school, basically, right?
I do not.
So yeah, you did answer it all, yeah, you wanted to. But we will derive it by definition. And then students tell me, why do I need to derive by definition? We know the derivatives of all the elementary functions. So first of all, we need to prove the derivatives of all the elementary functions. But
People actually ask you that.
all the time. And the next thing is that sometimes functions are not elementary. And one interesting thing that I'm not exactly studying, but I'm working on a video about is this. I'll give you the short version of it. This is a light wave. And this is bubble, like bubbles. In Hebrew we say what's sabon. Don't think
So bubbles.
It is soap bubbles. Okay, so it's soap bubble.
Fraction.
And the light travels at different speeds within different materials. So that makes the graph a bit different. And then the light wave come out of the other side. Agreed so far?
Mm.
What happens here is that this is the light. Oh, I need to change something for it to be. Okay, this is more interesting. I changed the width of the soap bubble. It actually makes a lot of difference. So the light wave is this, the blue one. That's the entering light wave. It does not equal to the green light wave. Do you agree? Why not? Because when the light wave reaches the surface, it splits into two. Part of it moves forward, that's that part here, and part of it goes backwards. Okay, that's a mirror basically. That's how a mirror works. Most of the light goes back instead of moving forward. Yes.
Why is it at different points in the entry?
That's the main thing. That's a very good question, but that's the main thing. Wait a second, okay? Then some of the light wave hitting the second part of the surface when going out go back, and some of it move forward. Okay? Altogether, when you sum them up, they look like this. And how can one tell what is exactly the part of the properties of the wave moving forward and moving backwards? How did I calculate all that? And the interesting thing is that nature has to be differentiable. It's the only solution which is differentiable. Does this point over here look differentiable, or does it look like a corner?
It's probably a corner. It is a corner.
I just said that nature demands differentiability. It looks like a corner, but it's not. You zoom in, you get it's actually differentiable. And that is the way. So all the different parts, there is only one way to part them, such that their sum will be differentiable. Because the actually electromagnetic fields is the sum of all the so-called parts of the wave. Yeah, that's the method. These parts are not, they do not exist in reality. In reality, you only have the green electromagnetic size of the value. So it has to be differentiable, and mathematically, it's like looking at different waves, and then you see, yes.
Slide looks to get so like that as well. Maybe that's just.
No, it has nothing to do. Okay, so I do have Sammy, is the light moving like this? Because I was always taught light is a straight line.
No, I'm asking when electromagnetic waves hit the surface.
If it hits on an angle, that's something else.
They get reflected.
That's
and they get what's called.
That's the Snell rule. If you hit the surface with an angle, then some of it is absorbed that way and some of it is returned that way. And the angles, again, are fixed so that the light wave travels differentiably in a differentiable way. Okay, so Snell's rule follows from the same demand. But here it's without an angle, it's easy. Yeah.
If I'm understanding it correctly, it means that the wavelength change between like the transition
Yes.
of materials.
Yes. But
But
you have to have the electromagnetic field always be differentiable. And
Yes,
that fixes
so
everything. Yeah.
You see it, that is magnetic or weak, but
That's physics. Right? There is an electromagnetic field around you which have values at each point and point. Some of it you are able to see. It's called light. Some of it you are not able to see, but it's still there, which is like I took out the phone because it's the cellular network.
radios.
Yeah, it's all part of the electromagnetic field. Okay. I'll just finish the thing.
Magnetic field is the entire spectrum.
It's everywhere. Every point has some value of the electromagnetic field. And if you look at this,
It's a state thing.
and if you look at a certain line in space, every point on the line has some value of the electromagnetic field. So what you actually see is the colored line here. It's easier for us to view the graph like so, but it's not actually going up and down. It's going more intense or positive or negative. So this is just a visualization, but when I'm talking about a ray of light, I'm talking about a line in space and measuring the size of the electromagnetic field at each point of this line, marked by color here. And I demand that it will be differentiable. Okay, and you can see here that the transition between the switch of the intensity is shorter here than here, right? And any question?
Do you think we?
Yes.
Yes, yes. But I really like it. I'm doing it along with a physicist. And the idea is to show that the mathematical concept that we study appear in nature. They weren't just thought of just to make students miserable. That's just a nice side effect. But these actually are real problems. And when I solve them, I made all this here. When I solve them, I use derivatives of patch functions. This is a patch function, and I solved the derivatives of it. And so I finished our time with that discussion. So next lesson I'll start by deriving the square root of x, and then we'll move on with the lecture. Have a nice day.
Do you think we need to make some extra lessons?
So far I don't think so. Let's